Hello, young minds. Our next topic embarks on a fascinating journey through the ages, the quest to unveil the secrets of chemical elements. Since times of old, curious minds have been uncovering elements like gold, which exist in their pure forms in nature. Imagine the amazement of our ancient counterparts as they stumbled upon these precious substances. But the story doesn't end there. Fast forward to modern times, and we encounter elements like technetium, which are inherently unstable and radioactive. Remarkably, our knowledge of these elements emerged thanks to advancements in 20th-century technology. This reminds us of the intricate relationship between scientific progress and technological innovation. As we proceed, keep in mind the immense significance of the periodic table, which organizes these elements and helps us comprehend their properties. Hello, young minds. Greetings, inquisitive minds. Our journey takes us to a true masterpiece of scientific organization, the periodic table. The genius behind this creation is Dmitry Mendeleev. He ingeniously arranged elements based on their atomic properties, which unlocked a new realm of understanding about the element's behaviors and characteristics. This arrangement forms periods and groups, each with its unique significance. Periods represent horizontal rows and groups form vertical columns. Elements within a group share similar properties, while those in a period showcase trends in atomic properties. The periodic table serves as our guide, revealing patterns that help us predict and comprehend the behavior of elements. It's a testament to human ingenuity and our pursuit of unraveling the mysteries of the natural world. Greetings. Welcome back, eager learners. Today, we're delving into the captivating world of electrons and how they shape the properties of elements. Electrons are like the dancers of the atomic stage. They dictate an element's behavior and characteristics. Particularly important are valence electrons, the ones found in the outermost energy level. These electrons influence an element's reactivity and bonding tendencies. How electrons are arranged within an atom, known as its electron configuration, holds the key to understanding why elements behave the way they do. Transition metals, found in the middle of the periodic table, bring their unique flair to the dance. Their electron configurations grant them distinctive properties, making them essential players in various chemical reactions. So, remember, the dance of electrons is at the heart of elemental behavior. Welcome back. Hello, curious minds. Our exploration leads us to a remarkable element, technetium. Discovered by Carlo Perrier and Emilio Segre. This element unveiled the world of radioactivity. Technetium is unique, not just because it's radioactive, but also because it doesn't occur naturally in substantial amounts on Earth. Its discovery came as a testament to human determination and ingenuity. Technetium-99 m, a radioactive isotope, is incredibly important in nuclear medicine. It's used for medical imaging, enabling doctors to peer inside the human body and diagnose various conditions. Think of it as a tiny, controlled source of radiation that helps us see and understand what's happening inside us. The story of technetium teaches us about the powerful relationship between science, technology, and the betterment of human health. Hello, curious. Hello, class. Today, we're embarking on a journey through the intriguing world of elements and compounds. You see, the majority of elements tend to combine with other elements to form compounds. This interesting phenomenon means that these elements are not usually found in their pure elemental form in nature. In fact, for centuries, scientists were quite unaware of the existence of these elements due to their tendency to form compounds. But as the early 19th century rolled in, chemistry made impressive strides. Scientists became better at isolating elements from their compounds, revealing their true nature. This marked a significant turning point, leading to a remarkable increase in our understanding of the elements. Just to give you a sense of the progress, imagine that in the year 1800, we knew about only 31 elements. Fast forward to 1865, and our knowledge had more than doubled, with 63 elements making themselves known. This rapid expansion of knowledge was largely thanks to the relentless pursuit of discovery by scientists of that era. Now, let's explore further. Hello, class. Hello, students. Today, we're embarking on a fascinating journey through the historical context of the periodic table. This journey will take us back to a time when the number of known elements was on the rise. As scientists encountered more and more elements, they realized the need for a systematic way to organize them. In the late 1800s, two brilliant minds, Dmitry Mendeleev in Russia and Lothar Meyer in Germany, independently devised classification schemes that shared remarkable similarities. They both observed a recurring pattern. When elements are arranged based on increasing atomic weight, similar chemical and physical properties tend to repeat periodically. What's intriguing is that during their time, atomic numbers were not yet known. Nevertheless, atomic weights generally increased with higher atomic numbers, allowing both Mendeleev and Meyer to arrange elements in a sequence that, by fortunate coincidence, closely resembled the correct order. Hello, students. Now, let's delve deeper into the contributions of Dmitry Mendeleev, a remarkable Russian scientist. In the year 1869, Mendeleev unveiled his revolutionary classification scheme. He ingeniously organized the elements based on their atomic weights, noticing a pattern of recurring properties. What's truly astonishing is that Mendeleev's approach was so comprehensive that he even left gaps in his table for elements that were yet to be discovered. And here's the incredible part. Mendeleev's predictions about the properties of these yet-to-be-discovered elements turned out to be astonishingly accurate. Now, Our journey also leads us to Lothar Meyer, a brilliant German chemist. In the same year, 1869, Meyer independently formulated a classification scheme that mirrored Mendeleev's approach. Like Mendeleev, Meyer arranged elements according to their increasing atomic weights. The similarities between their discoveries are astonishing and highlight the significance of the periodic arrangement. This parallel insight from different corners of the world solidified the importance of the periodic table in understanding the behavior of elements. Our journey also As our understanding deepened, the recurring patterns observed in the periodic arrangement gained even more significance. The advent of atomic numbers brought a new level of clarity to the table. Scientists realized that atomic numbers, representing the number of protons in an element's nucleus, directly correlate with an element's properties. The modern periodic table is organized based on atomic numbers, not atomic weights. This arrangement beautifully reflects the underlying electronic structure and chemical behavior of the elements, guiding us in understanding their properties and interactions. As we conclude this enlightening section, let's take a moment to reflect on the monumental impact of Dmitry Mendeleev and Lothar Meyer. Their visionary work laid the foundation for the modern periodic table, the cornerstone of chemistry and element classification. Their ability to discern patterns in the properties of elements and their foresight in predicting the behavior of yet-to-be-discovered elements is awe-inspiring. Their legacy continues to guide our exploration of the elemental world, enriching our understanding and pushing the boundaries of scientific knowledge. As we conclude, good day, students. Today, we're going to delve into the world of atomic structure and the brilliant contribution made by physicist Henry Moseley. Back in 1911, Ernest Rutherford proposed the nuclear model of the atom, which laid the foundation for our understanding of atomic composition. However, it was in 1913 that Henry Moseley made a significant advancement by introducing the concept of atomic numbers. Now, let's imagine a fascinating experiment involving high-energy electrons bombarding different elements. What Moseley discovered was truly groundbreaking. He observed that each element produced X-rays with a unique frequency, and interestingly, these frequencies tended to increase as the atomic mass increased. To organize this newfound knowledge, Moseley devised a brilliant solution. He arranged these X-ray frequencies in a systematic manner and assigned a special whole number to each element, calling it the atomic number. But what exactly is this atomic number? Well, it's the number of protons residing within the nucleus of an atom. This revelation gave birth to the modern periodic table, which we'll explore further. So, let's journey into the captivating world of atomic numbers and their role in understanding the building blocks of matter. Good day, student. Welcome back, eager learners. Let's continue our exploration of atomic numbers and their impact on the way we understand elements. Atomic numbers are like the identity cards for elements, they distinguish one element from another. And, do you know what's truly fascinating? Elements are arranged on the periodic table based on their atomic numbers. This arrangement is in ascending order, from the smallest atomic number to the largest. As you gaze at the periodic table, you'll notice columns and rows. Columns are often referred to as groups, and they contain elements with similar properties. This is due to their shared number of electrons in the outermost energy level. Rows, on the other hand, are called periods, and they showcase a pattern of increasing atomic numbers. This arrangement not only helps us organize elements but also reveals some intriguing trends in their properties. Now, let's dive deeper into the world of periodicity and explore how atomic numbers play a crucial role in understanding the behavior of elements. Welcome back. Hello again, inquisitive minds. As we journey further into the realm of atomic numbers, let's uncover some captivating trends. Atomic numbers wield immense influence over an element's properties. One of the mesmerizing patterns is the change in atomic size as we move across periods. As the atomic number increases, so does the number of protons and electrons. This, in turn, leads to a smaller atomic radius due to increased nuclear charge. Additionally, the arrangement of electrons in energy levels, guided by the atomic number, dictates an element's electron configuration. Keep in mind that as you traverse across periods, you'll notice an intriguing shift from metals to nonmetals. This progression significantly affects various properties, such as ionization energy. Ionization energy, the energy required to remove an electron, gradually increases across periods due to stronger nuclear attraction. Isn't it fascinating how atomic numbers play a pivotal role in predicting these trends and behaviors? Now, let's explore the depths of electron configurations and the mysteries they unveil. Hello again. But that's not all. Moseley's meticulous studies led to an even more exciting revelation. By examining the atomic numbers and their corresponding elements, he identified peculiar gaps in the periodic table. These holes were areas where elements were yet to be discovered. This newfound knowledge propelled scientists on a quest to find and synthesize these missing elements. Topic 4. Topic number 4. Heading: The impact of atomic numbers on modern chemistry. Bullet points. Atomic number is a cornerstone of modern periodic table. Resolving inconsistencies and predicting element properties. Foundation for understanding chemical behavior. Image. Comparison of Moseley's periodic table with the modern periodic table. Now, as we can see from the topic, the atomic number serves as a cornerstone of the modern periodic table. It played a crucial role in resolving inconsistencies and predicting element properties. This understanding laid the foundation for grasping the intricate chemical behavior of elements. The image on this topic presents a fascinating comparison between Moseley's original periodic table and the modern one. It visually demonstrates how far we've come in organizing and understanding the elements. But that's not all. Welcome, students, to our exploration of nuclear charge and its impact on electron configuration. By the end of this section, you'll be equipped to understand the factors that contribute to effective nuclear charge and its significance in determining various atom properties. We all know that atoms possess electrons, and the way these outer electrons are distributed plays a crucial role in the behavior of elements. As we delve into the subject, remember that Coulomb's law guides us in understanding the strength of interactions between electrical charges. It tells us that the magnitude of charges and the distance between them play a role in this interaction. Now, let's journey deeper into the captivating world of nuclear charge and electron behavior. Welcome. Hello again, young minds. Today, we're breaking down the foundation of Coulomb's law and its role in electron-nucleus interactions. Coulomb's law, a fundamental principle, guides us in understanding how electrical charges interact. This law reveals that the interaction strength hinges on the charges' magnitudes and their separation distance. In the context of atoms, the force between an electron and the nucleus relies heavily on the nuclear charge's size and the average distance between them. As the nuclear charge increases, so does the attractive force, and this force wanes as the electron ventures farther from the nucleus. Now, let's move ahead to see how these concepts shape the world of atoms. Hello again, young. Greetings, curious minds. Our journey continues as we focus on the intricate relationship between nuclear charge and the attraction force between electrons and the nucleus. It's crucial to understand that as the nuclear charge grows, the attractive force becomes stronger. This makes sense when you consider that a higher nuclear charge exerts a more significant pull on the electrons. Additionally, electrons tend to gravitate closer to the nucleus, and this proximity increases the force. On the other hand, as an electron moves away from the nucleus, the force weakens. Keep these ideas in mind as we progress through the fascinating world of atomic interactions. Greetings, well done, eager learners. We're now delving into the profound influence of electron configuration on the properties of atoms. Remember, the arrangement of electrons around the nucleus shapes how elements behave. The effective nuclear charge plays a pivotal role in this arrangement. It affects how strongly the outer electrons are pulled toward the nucleus, which in turn influences the atom's chemical behavior. Think of it as a dance between the nucleus and the electrons, determining whether an atom readily forms compounds or exhibits specific characteristics. Let's venture forth and explore the intricate interplay of electrons, charges, and atomic properties. Well done. Fantastic work, my diligent scholars. Let's take a moment to recap the key insights we've gained on nuclear charge and electron interaction. Remember, Coulomb's law guides us in understanding how the attractive force between electrons and the nucleus is influenced by nuclear charge and electron distance. We've learned that a greater nuclear charge leads to a stronger force, and as an electron moves away from the nucleus, the force weakens. This all ties into electron configuration, which profoundly impacts atom properties and behaviors. With this knowledge in our pockets, we're primed to journey further into the captivating world of atomic phenomena. Stay tuned for our next adventure. Fantastic work. Fantastic job, students. We've journeyed through the fascinating realm of electron-nucleus interactions within many electron atoms. To summarize, it's not as straightforward as in a hydrogen atom with just one electron. In this complex scenario, each electron must navigate both the pull of the nucleus and the push of other electrons. Electron-electron repulsions come into play, mitigating the nucleus's attraction and resulting in a net attraction that's smaller than what we might initially expect. This intricate interplay showcases the remarkable intricacies of atomic behavior. As we conclude this topic, keep in mind that the electron's journey within an atom is influenced by these opposing forces. Well done, and keep up the curiosity-driven learning. Fantastic job! Hello, dear students. Today, we're delving into an intriguing concept that helps us comprehend the interplay between nuclear attraction and electron repulsions. Imagine our electron of interest within an atom. We want to understand its behavior when faced with both attractive forces from the nucleus and repulsive forces from other electrons. The simplest way to make sense of this is by envisioning that the electron encounters a combined effect, a net attraction. This net attraction is the result of nuclear attraction, but it's decreased by the electron-electron repulsions. We've coined a term for this partially screened nuclear charge. The effective nuclear charge, ZEF. This value accounts for the modified attraction our electron experiences due to the delicate balance between these two opposing forces. It's crucial to recognize that because of the electron repulsions, the effective nuclear charge is always smaller than the actual nuclear charge, represented as Z. We can even express this mathematically by introducing a screening constant, S. In this equation, ZEF equals Z minus S, where S represents the screening constant that quantifies the degree of nuclear charge screening. So, we've got this fantastic tool, ZEF, helping us understand how electrons navigate the intricate landscape of atomic forces. Let's press forward to unravel more of these captivating details. Hello, dear students. Welcome back, inquisitive minds. Today, we're peering deeper into the dynamics between nuclear attraction and electron repulsions. Picture an atom as a dynamic arena where positively charged protons reside in the nucleus, eager to pull electrons closer, while the negatively charged electrons strive to maintain their distance, due to their mutual repulsions. In this tug of war, we introduce the concept of effective nuclear charge, ZEF. It's like a delicate compromise between these opposing forces. Think of it as the adjusted attraction and electron experiences. This adjustment is vital because the electron-electron repulsions counteract the full extent of the nuclear attraction. As a consequence, ZEF is consistently less than the actual nuclear charge, Z. This relationship can be expressed as ZEF equals Z minus the screening constant, S. This constant quantifies how much the electron repulsions dampen the nucleus's pull. It's truly fascinating how these intricate interactions shape the behavior of electrons within atoms. So, let's continue our journey of discovery. Welcome back. Greetings, curious learners. Today, we're uncovering the layers of the effective nuclear charge, ZEF, and its pivotal role in understanding atomic interactions. Imagine ZEF as a tightrope walker, carefully maintaining equilibrium between the nuclear attraction and electron repulsions. Our electron of interest is caught in this intricate balance, feeling both the pull of the nucleus's protons and the push from its fellow electrons. ZEF captures the net outcome of these forces, a net attraction. This attraction is influenced by the screening constant, S, which quantifies the extent of electron repulsion's impact on nuclear attraction. The relationship is elegantly summed up in a mathematical equation, ZEF equals Z minus S. Remember, Z represents the actual nuclear charge. An exciting aspect is that ZEF is consistently smaller than Z due to the presence of electron repulsions. This disparity showcases the complexity of atomic behavior and how electrons navigate their orbits. So, as we venture forth, keep in mind the delicate dance of forces shaping the atomic world. Greetings. Welcome back, students. Today, we're delving into a crucial concept in atomic structure called the shielding effect. This phenomenon plays a significant role in understanding valence electrons. Imagine you have an atom, and within it, you have various energy levels or shells. The innermost shells are occupied by core electrons, which are much closer to the nucleus. These core electrons shield the valence electrons, which are in the outermost shell, from feeling the full positive charge of the nucleus. This is due to the repulsive forces between negatively charged electrons. So, the value S comes into play. For valence electrons, S tends to be close to the number of core electrons present. While electrons in the same valence shell don't screen each other significantly, they do contribute slightly to S. This interaction among electrons within the atom has profound implications for the atom's properties. Now, let's dig deeper into this fascinating concept. Welcome back, students. Hello again, young minds. Our journey into atomic structure continues with the concept of effective nuclear charge, denoted as ZEF. Now, ZEF is a critical factor in understanding how valence electrons experience the pull of the nucleus. It's like the net positive charge the valence electrons feel after considering the shielding effect. You see, due to the presence of core electrons, valence electrons are shielded from the full nuclear charge. This reduced effective nuclear charge impacts various properties of elements, like their atomic size and ionization energy. As the number of core electrons increases, valence electrons experience a reduced ZEF, affecting their behavior and interactions. So, you can think of the valence electrons as both adventurers and shielded travelers in the atomic realm. They venture out to interact with other atoms, but their journey is influenced by the protective influence of core electrons. Fascinating, isn't it? Hello again, young. Good day, young scholars. Let's take a moment to appreciate the intricate dance that happens within atoms. Valence electrons, those lively participants in chemical reactions, are surrounded by their core electron companions. Core electrons act as the guardians, protecting the valence electrons from the full force of the nucleus. While valence electrons in the same shell don't shield each other significantly, they do play a minor role in our shielding story. This balance between the core electron's shielding effect and the valence electron's desire to explore and interact gives rise to the atomic behaviors we observe. Think of it as a dynamic interplay of forces that shapes the characteristics of elements and their ability to bond and form compounds. Keep this delicate equilibrium in mind as we move forward in our exploration of the atomic world. Good day, young Welcome back, eager minds. Let's dive even deeper into the concept of atomic shielding. As we journey through different elements, we find that various factors influence the degree of shielding experienced by valence electrons. One of these factors is the energy level or shell in which the valence electrons reside. Electrons in higher energy levels experience less shielding compared to those in lower levels due to their greater distance from the nucleus. This phenomenon has direct consequences for the size of atoms. Elements with more energy levels tend to have larger atomic sizes. This intricate relationship between shielding and atomic properties plays a crucial role in determining how elements interact with each other in chemical reactions. So, remember, the world of atoms is a realm of interwoven factors, and our understanding of them allows us to unlock the secrets of the physical world around us. Welcome back. Hello, curious minds. Now it's time to tackle the shielding puzzle head-on. Imagine an atom as a puzzle, with valence electrons and core electrons fitting together to form a complete picture. Valence electrons, though they venture to interact with other atoms, are never alone. They're surrounded by their core electron companions. These core electrons play a pivotal role in shielding the valence electrons from the full nuclear charge. And what's the key that unlocks this puzzle? It's the concept of effective nuclear charge, that net positive charge that valence electrons truly experience. This understanding allows us to predict properties like atomic size, ionization energy, and chemical reactivity. So, as we put the final pieces of our shielding puzzle together, remember that these concepts are like the secrets of the universe just waiting to be discovered. Hello, dear students. Today, we're delving into a concept that's crucial in understanding atomic structure: effective nuclear charge. To help us grasp this notion better, let's dive into an analogy involving a light bulb with a frosted glass shade. Picture the light bulb as the nucleus and imagine you, the observer, as the electron of interest, often a valence electron. Just as the amount of light perceived by the observer corresponds to the net nuclear attraction experienced by the electron, we can draw parallels. Here's where the analogy gets intriguing. The other electrons in the atom, especially the core electrons, play the role of a frosted glass lampshade. Their presence diminishes the amount of light, or nuclear attraction, that reaches the observer, our electron. Now, think about this. If the light bulb gets brighter, representing an increase in atomic number, Z, while the lampshade remains unchanged, more light is observed. Similarly, if the lampshade gets thicker, representing an increase in the number of shielding electrons, S, less light is observed. So, let's keep this analogy in mind as we explore the trends in effective nuclear charge. Hello, dear students. Today, we're delving into an intriguing concept known as effective nuclear charge, and its fascinating implications on orbital energies. Buckle up as we explore the hidden factors that govern an atom's behavior. The effective nuclear charge concept helps us understand how electrons are attracted to the nucleus. Think of it as the net positive charge an electron feels due to the nucleus after accounting for shielding by inner electrons. Now, let's connect this concept to the energies of orbitals. Remember our discussion on orbitals with the same n value? Well, it turns out that as we move from lower to higher values of L within these same n orbitals, their energies increase. To put it simply, electrons in orbitals with higher L values experience stronger repulsion from inner electrons, leading to higher energies. This phenomenon can be illustrated using the carbon atom as an example. In this atom, various electron orbitals showcase this energy trend. But fear not, we're here to guide you through the intricacies of this concept. Let's journey forward and unveil more about effective nuclear charge and its impact on atomic behavior. Hello, dear Good day, students. In today's lesson, we're delving into the fascinating world of electron orbital energies and how they're influenced by various factors. Our focus begins with understanding electron configurations. Take, for instance, the configuration 1 squared 2 squared 2p squared. Now, let's explore why the energy of the 2p orbital with 1 L is higher than that of the 2s orbital with 1 L, despite both being in the shell. This intriguing difference in energies can be attributed to the radial probability functions associated with these orbitals. To gain a clearer picture, refer to figure. You'll notice that the 1s electrons act as an effective lampshade for the 2s and 2p electrons, residing closer to the nucleus. Additionally, the 2s probability function features a small peak relatively near the nucleus, while the 2p probability function lacks this characteristic. This lack of peak in the 2p orbital results in a reduced screening effect by the core orbitals compared to the 2s electron. This difference in attraction between the 2s electron and the nucleus leads to a lower energy level for the 2s orbital as compared to the 2p orbital. This same principle applies to the general trend in orbital energies, such as 1 nanosecond squared 6 np to the power of 66 nd squared in many electron atoms. Now, let's proceed to uncover trends in valence electron ZeV values. Good day, student. Continuing our exploration, let's dive into the intriguing concept of valence electron ZeV values. The effective nuclear charge, often denoted as ZeV, plays a critical role in understanding the behavior of electrons in atoms. ZeV represents the net positive charge experienced by valence electrons due to the attraction from the nucleus and the shielding effect of inner electrons. Now, what's truly fascinating is the trend of ZeV across periods of the periodic table. As we move from left to right within a period, you'll notice a gradual increase in the effective nuclear charge. This trend is a result of the growing number of protons in the nucleus as we progress across the periodic table. This increase in ZeV has profound implications for the behavior and reactivity of elements within a period. It influences various properties, including atomic size, ionization energy, and electron affinity. Keep in mind that understanding trends in ZeV is key to comprehending the intricate interactions that occur within atoms and their elements. Now, as we delve deeper into our lesson, let's unravel more insights into the captivating world of atomic structures and properties. Continuing our Hello, dear students. Today's topic delves into the intriguing world of atomic structure, specifically focusing on the concept of effective nuclear charge and how it changes across periods in the periodic table. To better understand this, let's begin with a fascinating analogy involving a light bulb. Imagine the core electrons as the shade of the bulb, providing stability to the atomic structure. As we move across a period, something interesting happens. The number of protons increases, much like increasing the brightness of the bulb. However, the valence electrons added to counterbalance this increase in nuclear charge don't effectively screen each other. This is where our term, ZeV, comes into play. It represents the effective nuclear charge experienced by valence electrons. Let's take an example to make this clearer. Hello, dear. Alright, let's explore the example of lithium, Li. This atom has two core electrons that efficiently screen the valence electron located in the 2s orbital. Despite the increasing nuclear charge, the 2s valence electron is somewhat shielded by the core electrons. Consequently, the valence electron experiences an effective nuclear charge of approximately 3-2 = 1+. This balance between the shielding effect and the growing nuclear charge is a fundamental aspect of our understanding of atomic trends. Alright, now, let's shift our attention to beryllium, B. In this case, the atom still has two core electrons, but the valence electron count increases to 2 in the 2s orbital. The interesting part lies in how the core 1s electrons screen the valence electrons. The 1s electrons shield the valence electrons from a 4+ nucleus. However, each 2s electron only partially shields the other. As a result, the effective nuclear charge experienced by each 2s electron is approximately 4-2 = 2+. This variation in the effectiveness of screening contributes to the patterns we observe as we move across the periodic table. Now, let's shift. As we wrap up our exploration of effective nuclear charge and its impact on atomic properties, let's recap what we've learned. Effective nuclear charge, represented as ZeV, is the modified nuclear charge experienced by valence electrons due to core electron shielding. This shielding effect is crucial in understanding how valence electrons respond to the increasing nuclear charge as we move across a period. As we've seen with examples like lithium and beryllium, the balance between core electron screening and valence electron shielding contributes to the trends we observe. So, dear students, the next time you ponder the intricacies of atomic structure, remember how the analogy of a brightening light bulb helps illuminate the concept of effective nuclear charge. As we wrap up our Welcome back, students. Let's delve into the intriguing world of effective nuclear charge within groups of elements. As we move down a column, something interesting happens with the effective nuclear charge experienced by valence electrons. This change is far less pronounced compared to what occurs across a period. Take lithium and sodium, for instance. Using a simple estimation, we'd expect their valence electrons to encounter roughly the same effective nuclear charge, around 1+. But reality surprises us. The effective nuclear charge actually increases slightly as we descend a group. Why? Well, it's due to the unique nature of the electron cloud. The core electron cloud becomes more diffuse as we move down, making it less effective at shielding the valence electrons from the pull of the nuclear charge. Let's explore this concept further as we focus on the alkali metals, lithium, sodium, and potassium, and observe how their effective nuclear charge evolves within this group. Welcome back, students. Fantastic observations, students. Now, let's zoom in on the alkali metals, lithium, sodium, and potassium, and witness a fascinating trend in effective nuclear charge. In this group, as we progress from lithium to sodium to potassium, the effective nuclear charge increases. Lithium begins with an effective nuclear charge of about 1.3+. As we move to sodium, this charge becomes 2.5+. Finally, potassium takes the lead with an effective nuclear charge of 3.5+. But why does this happen? The answer lies in the electron cloud. As we descend the group, the core electron cloud becomes more diffuse. This diffuse cloud is less efficient at shielding the valence electrons from the powerful pull of the nucleus. Consequently, the valence electrons experience a stronger effective nuclear charge. This phenomenon showcases the intricate interplay between atomic structure and electron behavior. Let's keep exploring and uncover more gems of knowledge. Fantastic Brilliant observations, dear students. Now, let's shine a spotlight on a key player in the effective nuclear charge saga, the core electron cloud. This cloud plays a pivotal role in shaping how valence electrons experience the pull of the nucleus. As we journey down a group, the core electron cloud takes on a more diffuse character. This diffusion means that it's not as effective at shielding the valence electrons from the potent nuclear charge. Imagine it like this. Think of the core electron cloud as a protective barrier, but as we move down the group, this barrier becomes less dense. This phenomenon leads to valence electrons experiencing a stronger attraction to the nucleus, resulting in an increased effective nuclear charge. The subtleties of atomic structure are truly captivating, aren't they? Let's continue our exploration of the fascinating world of elements and their behavior. Brilliant observation. Marvelous insights, my brilliant learners. Let's recap our journey through the concept of effective nuclear charge within groups of elements. We've discovered that as we move down a column, the effective nuclear charge experienced by valence electrons changes, but with less variation compared to changes across periods. This change is influenced by the core electron cloud's behavior. As the core electron cloud becomes more diffuse down a group, its ability to shield valence electrons diminishes. This reduction in shielding leads to an increase in the effective nuclear charge experienced by valence electrons. We've seen this trend exemplified in the alkali metals, lithium, sodium, and potassium, where effective nuclear charge rises as we go from lithium to potassium. This intricate relationship between atomic structure and electron behavior ultimately impacts the properties of elements. Keep these takeaways in mind as we continue our exploration of the captivating world of chemistry and its underlying principles. Stay curious and keep up the fantastic work, my young scholars. Marvelous insight. Good day, students. Today, we're delving into the intriguing realm of noble gases and their unique properties. Let's begin by understanding what sets these elements apart. Noble gases, found in group 18 of the periodic table, possess some remarkable characteristics. One key feature is their fully filled s and p subshells, which make their electron configurations exceptionally stable. This stability is reflected in their large first ionization energies, which is the energy required to remove the outermost electron. As we move down the column, we notice a predictable decrease in ionization energy. But what's truly fascinating about noble gases is their reactivity, or rather, their lack of it. Due to their stable electron configurations, they are remarkably unreactive, earning them the name, inert gases, for quite some time. It was in the early 1960s that a breakthrough occurred, challenging this perception. Neil Bartlett, a researcher at the University of British Columbia, had an intriguing idea. He proposed that xenon, Z, an element from this group, might have a low enough ionization energy to actually form compounds. This was a groundbreaking concept that led to the discovery of noble gas compounds and expanded our understanding of chemical reactivity. So, remember, even the most stable elements can surprise us with their hidden potential for chemical interactions. Let's explore further. Good day, students. Now, let's delve into how the radius of an atom changes when it becomes a cation or an anion. Imagine you have an atom that loses electrons to form a cation. As electrons are lost, the overall positive charge of the nucleus becomes more dominant, pulling the remaining electrons closer. This leads to a decrease in atomic size. On the flip side, when an atom gains electrons to become an anion, the negatively charged electrons repel each other. This causes the electron cloud to expand, resulting in an increase in atomic size. Remember, it's all about the delicate balance between electrostatic forces and the number of electrons present. Now, let's take a closer look at the factors influencing atomic radii changes. At the heart of it all are electrostatic interactions, the forces between protons and electrons. Coulomb's law comes into play here, helping us understand how these charges influence the atomic size. The number of protons affects the positive charge of the nucleus, while the number of electrons dictates the overall negative charge. But remember, the inner electron shells provide a shielding effect. As we explore this intricate interplay, you'll gain a deeper appreciation for how atomic radii evolve in different situations. Let's take a closer look. We've covered quite a bit in this section, haven't we? Let's recap what we've learned so far. The periodic table is our invaluable tool for predicting atomic radius trends. We've explored how atomic size changes when atoms transform into cations and anions. Those electrostatic interactions between protons and electrons play a pivotal role. Remember, these concepts are fundamental to understanding various atomic properties. As we move forward, keep these principles in mind, as they'll serve as the foundation for our upcoming explorations into the intricate world of atomic structures. We've covered quite a. Hello, class. Today, we're delving into the fascinating world of atomic structure and size. Now, when it comes to atoms, it's easy to imagine them as small, solid spheres. However, according to the quantum mechanical model, this is far from accurate. In this model, atoms don't have well-defined boundaries where the electron distribution becomes zero. This brings us to the concept of atomic size, which we can define in various ways based on different situations. Let's journey into a scenario involving argon atoms in the gas phase. Imagine these atoms colliding with each other. Something quite similar to billiard balls colliding on a table. The interesting thing here is that the electron clouds surrounding these atoms prevent them from penetrating each other significantly. As a result, the shortest distance between their nuclei during these collisions is twice the radii of the atoms. This particular radius is known as the non-bonding atomic radius or the van der Waals radius. Now, let's explore this concept further and see how atomic size is shaped by the fascinating behavior of electron clouds. Hello, class. Welcome back, everyone. Today, we're delving into the world of molecules and the fascinating interactions that occur between atoms. What we recognize as a chemical bond is actually the attractive force between two adjacent atoms. We'll be exploring this concept more in depth in chapters 8 and 9. But, for now, let's grasp a fundamental idea. When two atoms form a bond, they come closer together than they would during a non-bonding collision. Think of it like atoms having a connection that keeps them closer. This leads us to a crucial term, the atomic radius, which is influenced by bonding. In our context, the atomic radius is defined based on the distance between the nuclei of bonded atoms. This distance is marked as d in figure 7.6. Moreover, we establish that the atomic radius for a bonded atom is half of this bond distance, d. Take a look at figure 7.6 to see how this works. Interestingly, the atomic radius differs between bonded and non-bonded situations, with the bonding atomic radius, also known as the covalent radius, being smaller. Keep in mind that when we talk about the size of an atom, we usually refer to its bonding atomic radius. Let's move forward and explore this captivating concept further. Welcome back, everyone. Hello, dear students. Today, we're unwrapping the concept of atomic radii and how they change when atoms form chemical bonds. Remember, the atomic radius is like an imaginary boundary that defines how close atoms are to each other. In our case, the bonding atomic radius, also known as the covalent radius, is derived from the distance between the nuclei of bonded atoms. Take a closer look at the bond distance, d. In figure 7.6, the bonding atomic radius is precisely half of this distance. Now, what's really fascinating is the difference between the bonding atomic radius and the non-bonding atomic radius. The bonding atomic radius is smaller because the atoms are drawn closer together by the bond. On the other hand, in a non-bonding situation, atoms collide and then move apart. This results in a larger non-bonding atomic radius. Keep these nuances in mind as we journey further into understanding chemical bonds and atomic interactions. Thank you for your attention, class. Hello, dear Welcome back, curious minds. Let's dig deeper into the importance of the bonding atomic radius. This concept isn't just about numbers, it's a key to understanding how atoms behave within molecules. The bonding atomic radius actually helps us gauge the size of an atom within a molecule. It indicates how close atoms are when they're bonded. Think of it as a measure of their connection distance. This concept is particularly valuable when comparing different atoms. By looking at their covalent radii, we can see how atoms of various elements fit together in different molecules. Remember, the bonding atomic radius plays a pivotal role in unraveling the mysteries of chemical bonds and how they shape the world of matter around us. Let's continue this exciting exploration. Welcome back. Hello, students. Today's topic delves into the fascinating realm of atomic distances within molecules and the concept of bonding atomic radius. Now, measuring the non-bonding atomic radius of an atom can be quite challenging. However, scientists have devised various techniques to measure the distances between nuclei within molecules. By observing these distances in numerous molecules, we can assign each element a bonding atomic radius. Let's explore this concept further with some captivating examples. Hello, students. This is an important concept, so let's dive in. Our example begins with the I molecule. Here, pay close attention to the nucleus-nucleus distance of 266 picometers. This measurement is crucial in our analysis. Now, this distance enables us to calculate the bonding atomic radius of an iodine atom within I. To arrive at this radius, employ this technique. Divide the observed distance by 2. After performing this calculation, we find the bonding atomic radius to be 133 pm. This piece of information is crucial for further analysis. Remember, mastering this process will greatly aid you in defining atomic sizes within molecules. This is an important. Now, let's move on to another captivating example. Diamond. Diamond is a three-dimensional solid network of carbon atoms. When we measure the distance between adjacent carbon nuclei in diamond, we find it to be 154 picometers (pm). Applying the same calculation method as before, we determine the bonding atomic radius of carbon in diamond to be 77 pm. This method allows us to gain insights into the atomic arrangement within solid structures. Now, let's move Moving forward, we arrive at the concept of defining bonding atomic radii for various elements. This is achieved by utilizing structural information from a vast array of substances, totaling over 30,000. This extensive data collection allows us to establish a consistent set of bonding atomic radii, as depicted in Figure 7.7. It's worth noting that for lighter noble gases, we must rely on estimations due to the absence of known compounds involving these elements. Moving forward. Hello again, students. Today, we're delving into the realm of atomic radii and how they play a crucial role in estimating bond lengths within molecules. As we can see in Figure 7.7, atomic radii provide valuable insights into molecular structures. Let's take a look at an example to solidify this concept. When it comes to the elements carbon, C, and chlorine, Cl, their bonding atomic radii measure 76 pm and 102 pm, respectively. Now, consider the molecule carbon tetrachloride. The actual measured length of the carbon-chlorine C0Cl bond in carbon tetrachloride is 177 pm. Interestingly, this length is quite close to the sum of the bonding atomic radii of chlorine and carbon, which is 176 plus 102 pm. This fascinating correlation highlights the significance of atomic radii in predicting bond lengths within molecules. Let's continue our journey through the intricate world of chemical interactions. Hello again. Greetings, curious minds. Today's exploration leads us further into the significance of atomic radii when it comes to estimating bond lengths within molecules. As we just discussed, the C-chlor bond length in CCl is remarkably close to the sum of the atomic radii of chlorine and carbon. Now, let's dig a bit deeper into why this correlation exists. Atomic radii are influenced by the distribution of electrons within an atom and the interplay of electrostatic forces. This means that as electrons are distributed in different energy levels around the nucleus, the resulting atomic radii can vary. Understanding these intricacies allows us to make educated estimations about bond lengths in various molecules. Keep these insights in mind as we journey ahead. Greetings, welcome back, eager learners. Let's take a moment to delve into the fascinating world of electron distribution and its role in bonding. As we've learned, atomic radii are influenced by how electrons are arranged around an atom's nucleus. Electrons occupy distinct energy levels, and atoms have a natural drive to achieve stability. One way they do this is by aiming for full valence electron shells. Bonding, whether through electron sharing or transfer, is a way for atoms to achieve this coveted stability. So, when we talk about atomic radii and bond lengths, we're essentially exploring the dynamic dance of electrons and their quest for equilibrium. Let's continue our journey through the intricate web of chemical interactions. Welcome back. Hello again, inquisitive minds. Our exploration now takes us to the captivating concept of electron sharing and its impact on bond lengths. When atoms come together to form molecules, they often share electrons to achieve stability. This type of bonding, known as covalent bonding, involves the sharing of electron pairs between atoms. Interestingly, the extent of electron sharing directly influences bond lengths. Greater electron sharing results in shorter bond lengths. But why is this the case? Well, the density of the electron cloud around an atom affects its size, and subsequently, the bond length. As electrons are shared more closely between atoms, the electron cloud becomes denser, leading to a contraction in atomic size and, consequently, shorter bond lengths. Isn't the world of chemistry truly mesmerizing? Our journey doesn't end here, so let's venture forth into more captivating territories. Hello again. Hello, students. Today's topic is a deep dive into the intriguing world of periodic trends in atomic radii. Atomic radii refers to the size of atoms, and it turns out there are some fascinating patterns that emerge when we examine these sizes on the periodic table. Let's get started with the first trend we encounter, within each group. As we move down a group, the bonding atomic radius tends to increase. This occurs primarily due to a fascinating concept called the principal quantum number, denoted as n. The outer electrons, which are responsible for bonding, are found in different energy levels or shells. As we go down a column, the principal quantum number increases, which means the outer electrons are farther from the nucleus. Imagine it like this. The higher you climb a ladder, representing the energy levels, the farther you are from the ground nucleus, resulting in a larger atomic radius. Now, let's move on to the second trend we encounter within each period. Here, the bonding atomic radius tends to decrease as we move from left to right, with a few exceptions. The main player causing this trend is something called effective nuclear charge, ZF. This might sound complex, but it's essentially the net positive charge experienced by the valence electrons due to the attractive force from the nucleus minus the shielding effect from inner electrons. As we progress across a period, the ZF increases. Think of it like a stronger magnet pulling things closer. In this case, the stronger ZF draws the valence electrons closer to the nucleus, causing the bonding atomic radius to shrink. So, remember, when going down a group, atoms get larger due to the outer electrons being farther from the nucleus, and when moving across a period, atoms get smaller due to the stronger pull from the nucleus. Keep these trends in mind as we continue to explore the fascinating world of atomic properties. Hello, students. Welcome back, students. Today, we're delving into the intriguing realm of ionic radii and the periodic trends that govern them. Just as we can determine atomic radii from interatomic distances in molecules, we can also deduce ionic radii from similar distances in ionic compounds. Now, when it comes to ion size, there are several key factors at play. We're talking about the nuclear charge, the number of electrons an ion has, and the orbitals in which its valence electrons reside. As we explore this, you'll notice that the formation of cations and anions has a significant impact on their sizes. When a cation is formed, electrons are actually removed from the atomic orbitals that are the most distant from the nucleus. This removal of electrons, combined with the reduction in electron-electron repulsions, leads to cations being smaller compared to their parent atoms. On the other hand, anions are created by adding electrons to an atom, resulting in increased electron-electron repulsions and causing these electrons to spread out more in space. As a result, anions end up being larger than their parent atoms. Keep in mind the dynamic interplay between these factors as we move on to our next point. Welcome back, students. Fantastic, learners. Now, let's dive deeper into how these trends in ion size play out across the periodic table. You see, where an element resides in the periodic table has a significant impact on the size of its ions. As we move from left to right within a period, we observe a fascinating pattern. The atomic size actually decreases, and this naturally affects the size of the resulting cations. This decrease in size is due to the increased effective nuclear charge that attracts the electrons closer to the nucleus. So, remember, as you move from left to right in a period, you're heading towards smaller cations. Now, when we travel down a group, a different trend emerges. The atomic size increases, and consequently, the size of the anions formed also increases. This increase is attributed to the additional electron shells being added as we move down the group. So, imagine this journey. You're going down a group, and the size of anions is going up. The periodic table holds so many clues to the wonderful world of chemistry. Fantastic. Brilliant work, class. Now, let's put our understanding into visual perspective. Take a look at this graph before you. On the x-axis, we have either the atomic number or the element symbol, representing the elements in the periodic table. On the y-axis, we have the ionic radius, which essentially indicates the size of the ions we've been discussing. As you observe this graph, you'll notice the periodic trends we just discussed come to life. Elements moving from left to right within a period show a consistent decrease in ionic radius, while elements moving down a group exhibit a clear increase in ionic radius. This visual representation beautifully encapsulates the dynamic nature of ion size trends. Keep this in mind as we journey forward in our exploration of periodic trends. Brilliant work, class. Good day, students. Today's lesson is going to take us deeper into the realm of atomic properties, specifically focusing on ionic radius and isoelectronic series. Our journey begins by exploring how the ionic radius changes as we move down a column in the periodic table. Think of it as a pattern. The ionic radius increases as the principal quantum number of the outermost occupied orbital of an ion goes up. This means that ions with the same charge become larger as we move down the periodic table. But that's not all. Let's dive into the concept of an isoelectronic series. An isoelectronic series consists of ions, each having the same number of electrons. For instance, consider the series O2, F, Na+, Mg2+, and Al3+. They all contain 10 electrons. Now, in any isoelectronic series, we can arrange the ions in order of increasing atomic number. And what happens as we move through this series? The nuclear charge increases, leading to a stronger pull on the electrons. And guess what? This results in a decrease in ionic radius. The electrons feel a greater attraction to the nucleus, causing the ions to shrink in size. Remember, the dance between atomic properties is truly captivating. Now, let's proceed to explore this concept further. Good day, students. Hello, dear students. Today, we're venturing into the captivating realm of space and the mesmerizing phenomenon known as auroras. Picture this. The Sun emits a continuous stream of charged particles called the solar wind. This wind consists mostly of electrons, protons, and alpha particles. Thankfully, Earth has a guardian, the magnetosphere, which shields us from this solar radiation. But, every so often, these two cosmic forces interact, creating an enchanting display of lights in the sky near the poles. These lights, known as auroras, are the result of excited atoms, molecules, and ions that come to life during these interactions. Let's dive deeper into this cosmic dance and explore the mysteries of solar wind and the auroras it brings forth. Hello, dear students. Welcome back, students. Today, we're unveiling the secrets of Earth's magnetic shield, the magnetosphere. Imagine it as an invisible, protective bubble that surrounds our planet. This shield is our safeguard against the continuous barrage of charged particles emitted by the Sun, which we call the solar wind. The magnetosphere skillfully deflects these particles away from our planet, preventing harmful radiation from reaching the surface. Without this protective layer, life as we know it on Earth would face significant challenges. So, as we explore further, remember to marvel at the wonders of our magnetosphere and its vital role in maintaining a habitable environment. Welcome back, students. Hello again, dear students. Today, we're uncovering the magical chemistry that occurs when the solar wind and Earth's magnetic field converge. When these cosmic forces meet, the solar wind's energetic particles collide with the gases in our atmosphere. This collision triggers a spectacular process. The atoms and molecules in the atmosphere become excited and release light as they return to their normal states. This mesmerizing display of lights, the auroras, paints the sky with a vibrant palette of colors. Different gases contribute to the various colors we see in these auroras. Isn't it fascinating how the dance between solar wind and atmospheric gases creates such breathtaking beauty? Hello again. Welcome back, my curious learners. Today, we're taking our exploration of auroras beyond the scientific realm. These celestial light shows have captivated human imagination for centuries. In various cultures, auroras have been woven into myths and legends, often reflecting beliefs about the divine or the supernatural. With the progress of science, we've gained a deeper understanding of the science behind these beautiful phenomena. But auroras aren't just a visual delight, they also impact our technology and communication systems. As we wrap up our journey into the cosmic artistry of auroras, let's not only marvel at their natural splendor but also reflect on the rich cultural tapestry they've woven throughout history. Welcome back, Hello, dear students. Welcome to a new section where we'll delve into the intriguing concept of ionization energy. By the end of this journey, you'll have a solid understanding of how ionization energy influences the behavior of atoms and ions. Let's start by defining ionization energy. It's the minimum amount of energy required to remove an electron from an atom or ion's ground state. Imagine this as the escape energy needed to liberate an electron from its home. We encountered a glimpse of ionization when discussing the Bohr model of the hydrogen atom. Remember how, when the electron in an H atom gets excited from its ground state to a high energy level, infinity, it's completely removed, and the atom becomes ionized? This is a fundamental concept. Specifically, the first ionization energy, denoted as 1, represents the energy needed to remove the first electron from a neutral atom. For instance, think about sodium. The first ionization energy for a sodium atom is the energy required for this process. Na becomes Na plus 1 G2 plus E. As we venture further, you'll realize how crucial ionization energy is in understanding chemical trends and properties. Let's dive deeper. Hello, dear Greetings, young minds. Today, we're unwrapping the patterns hiding within ionization energy. As you venture into predicting these trends, you'll open doors to understanding elements' reactivity and classifications. One crucial aspect impacting ionization energy is electron shielding and effective nuclear charge. Consider it as a tug of war between electrons and the nucleus. When electrons are farther from the nucleus due to added energy levels, they experience less attraction, resulting in lower ionization energy. But when electrons are close, the attraction intensifies, demanding more energy for removal. This brings us to trends. Generally, as we move across periods, ionization energy increases. Why? Because the effective nuclear charge grows due to more protons in the nucleus, overpowering electron shielding. On the other hand, down groups, ionization energy decreases. Why? Increased energy levels lead to electron shielding dominating, making removal easier. These trends hold the key to predicting chemical behavior, reactivity, and even the classification of elements. So, my curious learners, let's continue our voyage through the realm of ionization energy. Greetings, young. Ahoy, scholars! We're on a quest to unravel the real-world implications of ionization energy. Ready? Here we go. Ionization energy influences an element's electron configuration and bonding behavior. Elements with low ionization energy tend to form cations more readily, seeking to lose electrons and attain stability. Think of it as elements, eager to share. On the flip side, elements with high ionization energy are more likely to form anions by gaining electrons. This has a massive impact on how elements interact, combine, and create compounds. Ionization energy is a remarkable tool in identifying elements too. The distinctive energy values act as a fingerprint for elements, helping us recognize and classify them. Let's talk about noble gases. These remarkable elements boast exceptionally high ionization energy. Why? Their electron configurations are incredibly stable, and they resist giving up electrons. And don't forget transition metals. Their ionization energy varies across electron shells, which is a defining trait in their complex chemistry. So, as we journey on, remember that ionization energy holds the clues to the intricate dance of elements and their bonds. Ahoy, scholar! Dear students, let's pause and reflect on our journey through ionization energy. You've navigated the landscapes of energy needed to liberate electrons, and how it shapes the behavior of atoms and ions. You've uncovered trends that guide us across the periodic table, helping us predict reactivity and classification. You've seen how ionization energy plays the pivotal role of directing electron configurations and bonding preferences, influencing the stories of compounds. From identifying elements to understanding the noble gases' uniqueness and transition metals' complexities, you've gained a treasure trove of knowledge. So, let's celebrate your growth as chemistry enthusiasts. Remember, ionization energy isn't just a term. It's a key to unlocking the secrets of the chemical world. As we move forward, keep this knowledge close as it intertwines with other fundamental concepts in the wondrous realm of chemistry. Dear students. Hello again, students. Let's continue our exploration of energy concepts with a closer look at ionization energy. Ionization energy is a crucial concept when we talk about the energy required to remove electrons from atoms. Now, pay attention as we delve into the second ionization energy, often denoted as I2. This represents the energy needed to remove the second electron from an atom, and the pattern continues for subsequent electron removals. As an example, let's consider the sodium atom. Imagine we've already removed one electron from it, resulting in a sodium ion with a positive charge, Na+1. Now, what we're interested in is the energy associated with removing a second electron from this sodium ion, leading to the formation of Na2+1. This process involves energy changes, and understanding these transitions is key to comprehending the behavior of atoms and ions. So, remember, ionization energy plays a significant role in shaping the properties of elements and their compounds. Let's move on to our next intriguing topic. Hello again, welcome, dear students, to our exploration of ionization energy and its fascinating role in electron removal. Today, we're going to dive into the concept of ionization energy and understand how it's related to the process of removing electrons from atoms. Now, imagine ionization energy as a measure of the energy required to pluck an electron out of its orbital. The higher the ionization energy, the more challenging it is to snatch that electron away. As we take a look at Table 7.2, a pattern emerges. Ionization energies for a specific element progressively increase as we remove successive electrons. I1, I2, I3, and so on. This trend actually makes a lot of sense. Think about it, with each electron removal, the atom turns into a more positively charged ion. Consequently, it takes even more energy to pull away an electron from a positively charged ion compared to one that's less positively charged. This trend directly reflects the increasing difficulty in electron removal. So, let's journey further into the world of ionization energies and uncover the reasons behind these intriguing variations. Welcome, dear. Good day, students. Today, we're delving into the intriguing world of ionization energy and electron shell structure. Our journey begins by exploring a remarkable feature highlighted in Table 7.2. As we remove inner shell electrons, there's a notable and sharp increase in ionization energy. Let's consider the example of silicon, with an electron configuration of 1 squared 2 squared 2p to the power of 6 3 squared 3p squared. The ionization energies gradually rise from 786 to 4356 kJ per mole for the 4 electrons located in the 3s and 3p subshells. But what's truly fascinating is when we look at the removal of the 5th electron, originating from the 2p subshell. This process demands a significantly higher amount of energy, 16,091 kJ per mole, to be precise. The reason behind this substantial increase lies in the probability distribution of electrons around the nucleus. The 2p electron is more likely to be found close to the nucleus compared to the 4n = 3 electrons. As a result, the 2p electron experiences a much stronger effective nuclear charge, making its removal energy intensive. Now, let's delve further into the intricacies of electron configurations and ionization energy. Good day, student. Hello, dear students. Today, we're delving into a captivating topic that revolves around the interactions between electrons and atoms. Our focus is on ionization energy and its role in chemical bonding. You see, every element undergoes a remarkable change in ionization energy when its first inner shell electron is removed. This change serves as a cornerstone of our understanding that it's the outermost electrons that play a pivotal role in chemical bonding and reactions. In our upcoming discussions on chemical bonds, particularly in chapters 8 and 9, we'll uncover more about this fascinating phenomenon. It's intriguing to note that the inner electrons are incredibly tightly bound to the nucleus. This tight bond prevents them from being lost from the atom or even shared with another atom. This concept sets the stage for comprehending the complexities of chemical interactions. As we move forward in our exploration, you'll see how these insights form the foundation of our understanding of the atomic world. Hello, dear students. Welcome back, students. Now, let's dive even deeper into the pivotal role of electrons in shaping chemical behavior. The outermost electrons of an atom hold incredible significance. They are the ones that largely determine how an element will interact with other elements. When it comes to forming chemical bonds, these outer electrons are the stars of the show. Through sharing and transferring, they create the bonds that give rise to the rich world of chemical reactions. Our understanding of these interactions is deeply rooted in the concept of electron configuration. Just as each atom has a unique electron arrangement, These arrangements dictate how atoms will come together to form compounds. Isn't it fascinating how something as tiny as an electron can have such a profound impact on the entire realm of chemistry? Welcome back, students. Hello again, eager learners. Let's take a closer look at the inner electrons within an atom. While the outermost electrons are the stars of chemical bonding, the inner electrons play a vital but different role. These inner electrons are remarkably close to the nucleus and are held there quite tightly due to strong electrostatic forces. Because of this strong bond, they're less likely to be lost from the atom or shared with other atoms. As a result, when it comes to chemical reactions and bonding, these inner electrons take a bit of a backseat. Their stability and minimal involvement contribute to the overall stability of atoms. While they might not be the main actors in the chemical drama, their presence is essential for establishing the overall structure and properties of elements. Hello again. Greetings, inquisitive minds. Let's now piece together the fundamental elements of chemical bonds. Chemical bonds, the glue that holds compounds together, are forged through interactions between electrons. These interactions involve the sharing or transferring of electrons between atoms. The manner in which these electrons are shared or transferred determines the strength and nature of the bond. Remember, the electron arrangement, guided by the number of electrons in each atom's energy levels, plays a decisive role in shaping these bonds. This arrangement not only defines the bond's strength but also contributes to the various properties exhibited by different compounds. As we journey through the intricacies of chemical bonds, you'll discover the true marvels of how atoms come together to create a wide array of substances. Greetings, fantastic to have you with us, curious scholars. Now, prepare to delve even deeper into the captivating realm of chemical bonding. Our exploration will extend into chapters 8 and 9, where we'll unravel the complexities of various types of bonds. Two prominent types are covalent and ionic bonds. Covalent bonds arise from shared electrons, resulting in the creation of stable molecules. On the other hand, ionic bonds emerge from the transfer of electrons, leading to the formation of charged ions. Both of these bond types exemplify the remarkable ways in which electron interactions create the stability and diversity we observe in the world of compounds. As we move forward, you'll find that the universe of chemistry is truly a tapestry woven from the interactions of these tiny, powerful particles. Fantastic to have. Welcome, students. Today, we're delving into the intriguing world of ionization energy and its trends within the periodic table. Ionization energy, often denoted as I1, is a fundamental property that helps us understand the reactivity and behavior of elements. As we move across a period from left to right, you'll notice a consistent pattern. I1 generally increases. The alkali metals grab our attention with the lowest ionization energy in each period, while the noble gases stand out with the highest values. Now, don't be surprised if you encounter some slight irregularities in this trend. These deviations are like puzzle pieces that we'll soon fit together. Let's move on to our next point. Welcome, student. Now, my curious minds, let's shift our focus to the vertical movement within the periodic table. As we move down any column, you'll find a different trend emerging. I1 generally decreases. Let's take the noble gases, for example, helium, neon, argon, krypton, and xenon. Their ionization energies follow a clear order. Helium possesses the highest I1, followed by neon, then argon, krypton, and xenon. This trend highlights the progressive ease of removing an electron as we move down the column. Fascinating, isn't it? But wait, there's more to uncover. Now, Alright, dear students, let's zoom out and view the bigger picture. The periodic table isn't just a collection of elements. It's a canvas of trends waiting to be deciphered. In the S and P blocks, you'll observe a wider range of I1 values compared to the transition metals. The transition metals display a steady, gradual increase in I1 as we journey across a period. However, there's a special group that often stays hidden, our F block metals, not shown in the figure. These metals exhibit only a slight variation in I1 values. It's like they have their own secret code. As we continue our exploration, keep in mind that understanding ionization energy helps us predict how atoms interact and bond. Now, let's delve deeper into the realm of elemental properties. Alright,